his PhD degree actually in ETH Zurich here. And then after that, he joined TU Delft and as an associate professor working on the experimental soil mechanics. And he did a lot of work about soil interaction, pipeline soil interaction, and also static liquefaction. And after that, in 2022, actually this year, he relocated to Switzerland and joined the Swiss Federal Office of Energy. And he is working now in, I guess, mainly the design and monitoring of dam structures. So great, and the floor is yours. I mean, I think we have like around 35 minutes for the talk and 5 minutes for the questions. Thank you.
Good. Thank you very much. Good morning, everybody. Yeah, as Juan said, the topic is about monitoring and modeling of landslides, which are maybe triggered by rainfall. And I have a second title here: when a failure is a success. It might look a bit contradictory, but it's actually, this talk is the story of my part of my PhD project, which was done here at ETH. That's why I feel obliged to put the logo of ETH Zurich here. And as Juan said, I'm affiliated with TU Delft as associate professor, and also I'm working currently at the Swiss Federal Office of Energy. So yeah, I will very shortly talk about the motivation. I believe you all know about the risk of landslides. I do not need to convince you that it's an important topic, but I will show at least one case. Then I will talk about the methodology that we used for this research, and some examples of capabilities of physical modeling to gain some more detailed knowledge of these processes. Then, yeah, I will go more into the details about the field experiment, geotechnical centrifuges, and lastly, some conclusions. So about the landslide risk, on the left-hand side, you see the map of the world prepared by using satellite data by NASA. And they basically combine information regarding the annual precipitation, the intensities, return periods of various intensities, and also land use, land cover, and the amount of people and infrastructure being at risk. And as you can see, quite a large portion of the of our planet basically is under or has moderate to severe potential of landslides. We are now in Switzerland. I thought I will also show a picture of situation here in this country. On the right-hand side, you see the map of Switzerland. It's yeah, from east to west is around 380 kilometers, and these black dots, maybe you can see them, are basically, so whenever there was a landslide, mostly due to rainfall in Switzerland, we have very rarely landslides due to earthquakes here. And you can see that, yeah, whenever there was a landslide, researchers put a dot. And this is the database only from 1972 to 2012, which actually was produced or published by a group at ETH. And yeah, looking at these two maps, basically we see that, yeah, a lot of people have, on a more or less daily basis, some interaction with soil movements, or there is a chance to be affected by landslides. And with yeah, the current predictions of global climate change, we would expect actually to have, unfortunately, more dots on the maps at a higher rate in near future. And also the increase of population, attractiveness of mountainous areas to basically dedicated to some infrastructure or settlements. Therefore, we need to have a better understanding of triggering mechanisms. This is an example from Japan that the authorities actually could predict this landslide that is going to happen. Therefore, they blocked the road. And fortunately for us, they also put a camera that we can have a footage of this landslide. Because it was predicted very nicely, and they could basically know the extents quite well. there was no casualties associated with this. I have a YouTube video of that. I hope it works. Let's see. So you can see that it's a quite a large area that was affected by this, and then this road, yeah, if the authorities could not predict it well, would definitely pose an impact or a huge impact on the motorists on the way. Going back to the presentation, the second example that I just realized the video doesn't work is from Italy. That yeah, this landslide actually caused evacuation of about 200 people, and the cause was rainfall and unfavorable geological layering. We will think or discuss a bit more what these unfavorable geological layerings mean. So in very simple terms, landslide happens when the driving forces are larger than the resisting forces. And normally the driving forces are more known to us than the resisting forces, because soil is a complex material, and therefore we need perhaps to work a bit more on understanding the resisting properties of the soil, especially transient unsaturated soils. So looking at two grains that are below or located under the water table, we have these repulsive forces of pore pressure, basically. That basically these pore pressure forces are acting in all directions, perpendicular to all of these grain surfaces, and basically in fully saturated condition, this repulsive work is or repulsive force works in a way that the two grains are moving away from each other. So basically, if we look at the definition of effective stress, it's total stress minus pore water pressure. But when we have negative pore water pressure, or the grains are located above the water table, and there is some residue of moisture in between the grains, these so-called menisci would form, and these menisci actually can resist some tension, as you can see here in this nice microscopic picture from 2004. This distance is 30 microns, and these two grains actually could sustain some tension, and this is basically the cause that a lot of the slopes are stable and become unstable when it rains. So when we move from this situation to fully saturated situation. In terms of equations, or how we can mathematically in a very simplified way describe this phenomenon, you know all about the shear strength of the soil, which is a function of effective stress. But in this equation, basically for unsaturated soils, we separate the effect of total stress and the suction. So the first term is basically the so-called total stress minus pore air pressure, and the second term is called the apparent cohesion. So basically, this is not related to the total stress; it's purely related to the amount of pore water pressure. And this parameter chi is basically a function of degree of saturation. A lot of researchers, for simplicity, they just assume that this value of chi is just equal to degree of saturation. So when it rains, basically, before rainfall, this UW, so the pore water pressure is negative. So we would have a larger value of apparent cohesion, and as the rainfall commences, and we have some lower negative pore water pressure in between the grains, this term basically reduces, and in fully saturated condition, it goes down to zero. But of course, that is just looking at two grains, but in reality, we have a very complex situation. So if we want to predict a landslide is going to happen in a region or not, there are a lot of points that we need to look into. The first one, for example, is that in a lot of cases, we assume that the bedrock is parallel to the slope surface. And in most of the cases, actually, it's not the case. Also, bedrock, we normally assume that it's impermeable, but not only it's not impermeable, but also sometimes you have this unfavorable geological layering that we would have actually some water coming out of the bedrock, and this is called exfiltration. The bedrock might have a dip in the shape, so therefore you might have some locally saturated zones as well, or you can have some lenses of soil with different permeabilities. Therefore, you have a really complicated interactive system that if you want to basically make a prediction for a landslide, you need to take into account. So the major questions that in these sort of studies we need to take into account, firstly, is that what are the hydromechanical responses of the ground to rainfall? So if you have a slope, what would by hydro, I mean how the pore pressures change, and mechanical means that how the effective stress and hence the shear strength changes, and also maybe some volumetric changes. The second question is that especially important for authorities is that can we have some indications of the failure before it fails, of course. Not only indications about the time, but also indications about the volume and also the runout. So about the timing, there are a lot of research that you might be aware of, is this keyword early warning system that is basically based on measurements and understanding the soil behavior to interpret those measurements. Then a bit more on the interactions, what I mentioned about the geology and hydrogeology interactions with the soil mantle is important, and also what recently has, I mean, since a couple of decades ago, but recently, maybe during the past 20 years, has taken up is about the effect of vegetation. So there are, of course, many different ways to study this process. What I did during my PhD was so the main question is about the triggering mechanisms of landslides induced by rainfall, and you can approach it in several ways. You can have a physical modeling, basically, to perform a full-scale test or a geotechnical centrifuge test, or you can have analytical models. For example, limit equilibrium method, or you can have some numerical modeling. And the main point that basically needs to be done very well is the characterization of the soil, which basically feeds to these two approaches. And in order to understand what we see in physical modeling and what we see in the numerical and analytical models, basically we need to have a very good interaction between these two. So just visually, soil characterization can be done in many ways. What I did, I used a large triaxial test done together with Alex Marin, who is here. He actually took these pictures. Then we can perform some full-scale tests. I'm going to talk more about this. We can perform some centrifuge tests, and of course, some numerical modeling. So let's have a look at the field experiment. We chose a slope which was located in the northern part of Switzerland, in the beautiful canton of Schaffhausen, at the banks of River Rhine. So this is an aerial photograph, so you can already see that. So this is our test site. This is a River Rhine flowing from canton of Graubünden all the way going to Germany. And you can see already from this figure that there are some signs of movements in this region. Of course, Rhine has eroded the toe of these slopes, and therefore you have some retrogressive landslides, and you can see this depression in close to the village, which is called Buchberg on top there. You can see also some signs here and some others here. And also you can see some signs of shallower landslides along this very beautiful hiking route. So if you are here tomorrow and the weather is good, I can really recommend this to have a look. Some more obvious signs of movement in this region. You can, for example, see that the trees are not always vertical. And this is a sign, so you can see that they are bent, and this is a sign that actually the base has been moving downward. So it's a creeping slope along the banks of River Rhine. Or you can see some outcrops that basically this bedrock has been exposed. So the soil on top has slid down. Some very obvious signs of previous landslide. So, for example, this is a landslide or series of landslides that happened in 2002 in this region after 100 millimeters over 40 minutes. This was really an extreme case that happened, and you can see some cracks at the base of this house here, and some mudslide basically occurring in this region. So starting with the first part, which is the soil characterization, the first thing that we did was to go and take some samples completely disturbed and do grain size distribution. So we took samples from different depths of this slope that I'm going to explain which slope it is, but it's in Dridlingen. And you can see that, it's according to the unified soil classification system, it's medium to low plasticity silty sand. We performed a couple of conventional consolidated drained triaxial tests, and constant volume internal friction angle was calculated or measured to be 32.5 degrees. And I also performed some more advanced stress paths that I'm going to explain a bit more in details. And the internal friction angle at failure was measured to be 36 degrees. So for these advanced stress paths, I thought maybe I explain shortly what I mean by those. So basically, when you have an element of soil in a slope already, because it is located on a slope, you have shearing on this element. It's not failing, but it is not without shearing. Therefore, if you want to prepare your sample, you need to consolidate it in an isotropic way. So you have already sigma 1, which is different to lateral stresses. And basically, you consolidate the sample in this anisotropic condition. And to simulate the rainfall, basically, you simply increase the pore water pressure in your sample while keeping the boundary conditions in terms of stresses constant. So maybe I ask the public a question. What happens to this more circle when we are simulating this rainfall of this triaxial sample? Does the radius change? Does it move? The radius does not change? Pore pressure changes. We are injecting water to simulate the rainfall. The total stress remains the same.
Okay, so it's moving.
Very good. So it moves to the left, right? Because we are increasing the pore water pressure, effective stress decreases. So basically, we expect that these more circles in this tau sigma dash space basically moves to the left. And according to previous conventional triaxial tests, we expected this stress state to be the failure at as soon as it touches the failure envelope with a phi dash of 32.5 degrees. But surprisingly, we saw that actually it didn't fail, but it went a bit further. So actually, because of the lower stresses, we have a tendency for dilation. Therefore, the slope actually was a bit more stable. I had prepared another question, but I leave it for you. But anyway, I'm going to explain it. So in order to look at this in P-Q space, I have basically drawn the results in this space here. So P dash is the mean effective stress, so the average of sigma 1, sigma 2, and sigma 3, and sigma 2 and sigma 3 are the same in this case in the triaxial condition, and Q is the sigma 1 minus sigma 3. So if we start from this point here, that's the initial point that we are increasing the pore water pressure, so the rainfall is basically in progress, and this red dash line is the envelope or failure criterion from CD test, so conventional consolidated drained triaxial test. And we see that both of these two samples, so one of them a bit looser than the other one, went beyond this failure criterion and then failed, both of them more or less at an eta failure of 1.47, which is equivalent to a phi dash of 36 degrees. And this is indeed because of the lower effective stresses and the tendency for dilation. So unfortunately, I don't have much time to explain about the soil characterization, but at the end of presentation, I have put some, I've listed some references for those who are interested. Of course, for this sort of questions, the hydraulic properties of the soil are very important. So, for example, unsaturated conductivity or water retention curves that we measured, but due to time constraints, I cannot explain now. So this is the slope that we chose to basically fail to induce this artificial landslide. And as you can see here, it has a width of 8 meters, an on-surface length of 30 meters, and an inclination of 38 degrees. Just by limit equilibrium conditions, this angle is higher than the internal friction angle, so either 32 or 36 degrees. Therefore, it should not be stable according to classic soil mechanics, but it is stable, and we wanted to know why. On the right-hand side, you see the geology. We performed some geophysics and also some mechanical tests to look at the shape of the bedrock. And you can see the bedrock is actually laterally inclined. So looking upwards, we can see that on the right-hand side, it's shallower than the left-hand side. And also we realized that there were some features in the bedrock. There was a so-called buttress at the base, so accumulation of old rocks, basically. And also a permeable layer that you will see later on. We didn't know actually this existed here. We performed some monitoring. Suzanne mentioned about TDRs, time domain reflectometers. These are really excellent and simple instruments to monitor the evolution of degree of saturation of the sample, or not exactly degree of saturation, but volumetric water content. So if you know the porosity, you can calculate the degree of saturation. So we installed basically in 3 so-called clusters these series of, or we installed these sensors, TDRs from depth of 15 to 150 centimeters. And then we, using piezometers, we measured exactly at the same horizons the value of suction. We measured the surface and subsurface deformations. I will come back to this a bit later. We also measured how much of the water that we are artificially raining is going into the soil and how much of it is runoff, basically. And then also we had installed piezometers. So this is the slope before we did the rainfall. So you can see that we had put these pedestals here with sprinklers, and you can see a huge a body of cables running around and all going to this data logger here. A bit about the geology. So here you can see the general geology of this slope. On the upper part, we have so-called upper seawater molasse, and on the lower part, we have the lower freshwater molasse. And basically, it's sandstone with some marlstone, so clay layers here. And in the lower part, we saw quite large joints because when the river Rhine was flowing, maybe I show it here, when the river Rhine was flowing, basically it decreases the sigma 3, so the lateral confining stress, and these joints opened up. And sometimes you had joints which were around 10 centimeters in width. So they can really work as a very good and efficient drain into the geology. Also here on top, because we have a change in the geology and the permeability of the layers, you could expect some water coming out of the out of the slope. And in winter, it was in January 2009 that I went to visit the slope, and I could see really one horizontal layer of ice basically forming at the interface between these two layers, so the upper seawater molasse and the lower freshwater molasse. To confirm that, we performed some geophysics, so electrical resistivity tomography. And the figures that you are seeing here, or the colors that you see here, basically are the values of electrical conductivity of the material. Electrical conductivity is dependent on two parameters in the soil. One of them is the amount of water that is in the soil. The other one is the amount of ions that you have in the soil. So if the soil is more saturated, then you would have lower resistivity. And if the soil has more ions, so for example, you have clay, then you would have also lower resistivity. So here, when we look at this figure, we can see that the upper part has a bit less resistivity, higher resistivity, and in the lower part, we can see that there is less resistivity. This is the area that basically the marlstone was intruded into the sandstone. And then there was some extra intrusion of the sandstone into the marlstone as well. One of our colleagues, Massimiliano Schwarz, who is now a professor in Switzerland, he did a very good job in characterizing the root reinforcements at different locations on this slope. And he basically developed a device that could basically pool the roots and measure the tensile resistance of them. And so basically, he mapped the root reinforcement on this slope. One of the important points that I explained at the beginning is about the early warning systems. And early warning systems basically work based on measurements. And one of the very important measurements is the displacement. And what we wanted to know is how much volume would be mobilized when we have a failure. So it means that we need some subsurface measurements of the displacement. And in order to know that, we need to have a sensor. The conventional method is to use slope inclinometers, that you have a casing and you put a trolley which has some accelerometer or tilt meter installed on it. And every now and then you stop when you are driving it, and you measure the tilt. This is a very accurate measurement, but it's manual and it's very slow. When we look at previous experience about landslides in silty sand material, so for example, this case in Japan, Professor Ochiai, about 4 years before our experiments, they did this experiment, a very amazing experiment that they did on the hills. And they saw that within 3 seconds, 17 meters, so the soil moved for 17 meters, so very fast movement. Also, Andy Take in Cambridge on the same year, more or less on the same material, performed some centrifuge tests, and they realized that actually their high-speed camera was not very high speed, so they could not detect the movements of the grains very easily. And also 2006, 2 years later, Professor Piccarelli in Napoli performed some tests, and they also saw some immediate and very fast movements. So what these experiences told us was that a normal inclinometer is not going to work.
What soil is it?
Silty sand. Yeah. So we realized that, the normal slope inclinometer is not the way to go because, I didn't want to be on the slope when it wants to start failing. So what we did, we developed a sensor that is called the slope deformation or soil deformation sensor. And it's very simple. It's basically a flexible aluminum plate, and along it, we installed pairs of strain gauges. The lower part was fixed with mortar into the bedrock so that it gives us a mathematical fixed point. So there is no rotation, no displacement. So we could make integral of the bendings. And knowing the bendings, we could basically get the subsurface deformations. Also, knowing the bendings, theoretically, basically, we would say that the negative bending, so when the lower fibers of this cross section are in compression, we call it negative bending. And when we have a change in sign of bending from negative to positive, that is more or less the location of the failure surface. We performed some large scale tests in the lab, and we could confirm this hypothesis. So basically, maybe I explained this. The only thing that I forgot to explain is that we measured it at very high frequency. So 100 samples per second from 4 soil or strain inclinometers from each of these strain bridges. In terms of bending stiffness, so if we compare the bending stiffness of this deformation probe with normal casing of the strain inclinometers, we see that it's flexible by a factor of 300. So it means that you can actually detect much finer movements in the slope comparing to normal slope inclinometers. And also one point that perhaps is good to mention is that with bending strains, we can, and knowing one fixed integration point, we can calculate the deformations. Knowing the deformations, you can have the velocities and accelerations. So to October 2008, we went to the field and started the water, and we applied a series of drying and wetting cycles, what Susan was mentioning, on this soil or on this slope, with some really strong intensities. So, for example, here you can see that we went all the way to 65 millimeters per hour, but just for a couple of minutes, not for long, to simulate intense rainfalls. It was really an informative test. We could gather really high quality data, but it was very disappointing because there was no failure. And we had promised the Gemeinde, the community, that we are going to make a failure in their in their garden, but it didn't work. So it was a bit of a disappointment. A lot of thought went into what went wrong, or what could have been done better. So what we realized is that it's better, or it would be better, to put the sprinklers on the upper part of the slope, because the source of water was on top, and actually the sprinklers discharged more water towards the lower part, where we had more roots, so more root reinforcement, and also a lot of fissures in the bedrock. So that was the first thing that we discussed, or we changed. The second thing was that, as you see, there are a lot of trees along the perimeter of this slope. So what we did, we basically went with a shovel and cut the tree roots, basically, along the longitudinal edges of the slope. So to have a more or less plain strain condition for the first 30 to 40 centimeters of this slope. And then in March 2009, we went again with a lot of energy, and this was the result. maybe I explain to you what we see here. So this is from one of our photogrammetry cameras that we had installed on tall trees in front of the slope. And this area is the down slope. This is the upper slope. You can see that the sprinklers are more concentrated on the upper part of the slope. And we needed to put these styropor spheres, markers, stick them into the ground to have some points to track, basically, using these photogrammetry cameras. Also, this line here, this is a dynamic electrical resistivity tomography line. So we had electrodes every, I believe, half a meter, and we injected voltage to measure the evolution of the resistivity, which means evolution of saturation inside the slope, to basically have a redundancy in measurement of saturation with regard to TDRs as well. So let's see what happens. So this is just a couple of seconds before the failure. You can see that the failure started on top, as we had expected it, because the bedrock was shallow and also less root reinforcement. It comes in steps, and then it suddenly accelerates. And of course, it pulls all of the cables. So we have lost some of the last measurements before the final failure. Maybe I go back quickly just for you to have another look. We measured the final, or approximately measured the final velocity, and it was more than 10 meters per second. So you need Usain Bolt to run this landslide. Otherwise, there's a big danger over there. So what we see here is that there is water coming out of the bed, I mean, from the bedrock on the back of the slope, and also at this point here. Maybe if I run it, you can see that there is water actually coming out of the bedrock. I have a bit higher resolution photo. So these were slow but high quality images that we took. So these are the locations of these strain inclinometers that we had installed on the slope. And the same figure basically when the failure happened, and you can see water coming out at these locations. So let's have a look at the results of one of these strain inclinometers that basically we gathered together and installed them. And you can see that the y-axis is the depth, the x-axis towards the left basically is the amount of deformation. And you can see that we started rainfall at about noon on 16th of March 2009 until about 3 hours later, we didn't see much meaningful deformations. The first real deformation basically happened at midnight, so about 12 hours after the rainfall. And you can see that the failure basically most probably was at a depth of about 50 centimeters, so very shallow failure. This kickback is basically an integration error that happens due to the stiffness of this sensor. But then we see that at about 1:30, so about 13.5 hours after the start of rainfall, a huge or a very strong, deeper failure surface has evolved, and you can see that you have a pretty clear shear band forming at this depth. So at about 1.4 meters from the soil surface. And then this is the last measurement that we have at 3, or last reliable measurement that we have from this sensor at 3 in the morning. The final failure, what I just showed you, was at 3:23. So we see that, the failure depth is at 1.3. And then after, the day after, I went just to make sure that these, because all of these are based on strain measurements. So I went and looked at the sensor, and it was in fact bent at that location that was predicted based on the strain measurements. So, but we can get some more information from these bendings, and the first one, first maybe I explain the results of the piezometer. So here you can see that on top we have piezometric heights. They started from 0 where the sensor was, and when the water came, the perched, so-called perched water table basically got formed. Excuse me. And they went up and stayed stable until a certain time. Very surprisingly, we saw a drop in the measurements of the pore water pressure or the water table head. And when we look at this, we see that actually this lower graph, maybe I explained it first, is the amount of external bending work per unit volume of these sensors that we have installed. In other words, it means the amount of energy that is exerted due to movement of the landslide on these bending elements. So you can see that this value basically reached the peak more or less at the same time that the soil started to have a more dilative behavior. So the pore pressure basically decreased. So this is in line with what we saw in the triaxial cells as well, that the sample or the element that we tested actually showed at very low effective confining stresses a dilative behavior. But anyway, because the rain is still running, the pore pressure cannot basically, or the decrease in the pore pressure due to dilation cannot increase the strength that much, and anyway we got a failure. This could be one of the indications for early warning system. So about 2 hours before the main failure, this happened. So basically, this was the first physical modeling that I wanted to discuss. But what we learned from these and what other points we can further discuss or understand using centrifuges. The first one is that as you see, the bedrock is not parallel to the soil surface. There is this accumulation of old boulders at the base. We wanted to see, and in the first experiment, we saw that the concentration of water was actually in the lower part, where we have this so-called buttress effect of the bedrock. So we wanted to basically quantify this effect with centrifuge. The second thing is about the drainage into the bedrock. The third one was the effect of the roots, and the last one about the exfiltration from the bedrock. So centrifuge, this is a sketch from the time that this was the best I could do with AutoCAD. My AutoCAD skills were not that good, but anyway, it gives you an indication. So we wanted to make a slope of 38 degrees. We wanted to apply rainfall, and we wanted to also apply cycles of wetting and drying to this slope. So basically, we applied rainfall. We also could simulate the wind to basically simulate evaporation. We had lights, again, to promote evaporation and also give information for, or give enough light for our cameras. And also we measured temperature and humidity. I performed the tests in the drum centrifuge here at ETH. I don't know if you had a chance to see that. No, but yeah. So this is the drum centrifuge that. It's closed there. Yeah. Drum centrifuges are excellent, but they have one tiny but very important question, that you have this 1G from the beginning. And if you want to install your sample, you need to, from 1G, rotate it and then put it on this channel. We have really excellent technicians. The lead of the centrifuge is Marcus Eaton, and he found a very good way to overcome this. But anyway, in order to basically simulate rainfall in the centrifuge, I needed to do quite a lot of modifications to the centrifuge. The first one was that, I needed water. So I needed to build a central water tank in our tool table. Then I needed to pressurize it to make sure that I have enough flow of rain or intensity of rain. There were some other very complicated electronics and valves that our electrical technician Ernst Bleicher really helped me with. And this is how it looks like in the centrifuge. So I have these two already 90-degree tilted boxes with the slope inside, and this is the tool table. And I want to just very shortly mention what we need to do in order to basically simulate rainfall in the centrifuge. This lower blue box that you see here is the original box that we had at ETH. Then I realized that in order to apply rainfall, apply wind, and also do measurements, I need some extension. So we designed these extension pieces. And then what comes on top is important. So on top we have basically these two top plates that host the photogrammetry cameras, also the air valves to promote the flow of the wind, basically. We integrated channels to basically install nozzles and simulate the rainfall. So looking at the detail of this top plate, basically I designed an inner channel with 4 nozzles. And also soon I realized that because of Coriolis effect, we might need some external channel. Therefore, I designed together with Marcus an external channel with 18 nozzles. So by opening and closing these nozzles independently, we could basically reduce the effect of Coriolis. One of the major points that we wanted to basically study was the interaction between the bedrock and the soil. So we needed to integrate quite a lot of details into the bedrock as well. So we have some so-called exfiltration simulators that we could inject water from the back of the bedrock into the soil. We have this semicircular or this arc of buttress to simulate uneven shape of the bedrock. And also we had some sensors to monitor the suction development in the slope. Sam, yesterday, I'm sure, gave you all of the details about the PIV, but also we also did some PIV there. And what I want to mention here is that because in the centrifuge, normally for these cases, you have a 3D shape. You don't have a full plane strain failure. So I installed the photogrammetry cameras in order to monitor this 3D shape. It was really a challenge because you need to very carefully get out of the distortion due to these the lens of these cameras. Therefore, we needed to do a series of rigorous calibration of these cameras. And this is one of the tests that you can see that we have a failure, not really plane strain. It's completely 3-dimensional, and we could really get a very good view of the details of the surface when it failed with all of the pictures that we took. So what tests I performed? I performed a test that the bedrock is parallel to the slope. We opened the channels inside the bedrock in order to simulate the drainage in the bedrock. Then we simulated exfiltration and also the different shape of the bedrock. But unfortunately, I don't have time to speak about those. I thought maybe I just show you.
It was intentional.
Yes, it was intentional. Yes. So we needed, or we wanted to know the effect of roots in the soil, so the reinforcement effect. So what I did, I basically planted roots in a very a clear raster on the slope. And I studied the roots very carefully. So I had, I think, 90 seeds and statistically measured the length of the roots and the shape and also the pattern of the roots. I think 90% of them had only 3 main roots. And at the same time, when I planted this and watered them every day under complete controlled humidity and temperature conditions and light conditions, at the same time, in the same room, I also planted them in a direct shear box, so a large direct shear box that we have at ETH. Every day I needed to plant to water both of them. And on the same day, I performed the shearing on this sample and also in the centrifuge. So because we are dealing with biological effects here, so in order to minimize all of the side effects that we can have. So very short detail about the root reinforcement. Basically, these root reinforcements add to the tensile strength of the material, and we can show it by an increase in the a shift upwards of the failure envelope. So basically, if we don't have any roots upon wetting, this Mohr circle, as you saw in the first part of the presentation, would hit this failure envelope at here. But if we have some root reinforcements, this Mohr circle can go a bit more to the left. This is the results of the direct shear test that I performed on the root reinforced, and you can see indeed there is a shift in this line in this sigma dash tau space. Very shortly about the centrifuge results. So here on the x-axis you can see the time. This is the scale time in reality. So n to the power of 2 basically. That's why you see it's 6,000 hours. And on the left vertical axis, you can see the average displacement. So using these photogrammetry cameras, I could calculate the on-surface displacement of the slope or of the particles on the slope. And you see that for the sample without vegetation, after about 600 hours of rainfall at an intensity of 1.27 millimeters per hour, I got a failure, and it failed basically the slope. But the red curve basically shows me shows us the results of the sample with vegetation, with just 4 kPa increase in the vegetation due to the vegetation. You can see that I went all the way to around 2,000 hours of rainfall, again in prototype scale. Then I needed to wait because all of the water was gone. I didn't have any rain, so I needed to stop the centrifuge, fill up the water tank, and then again, you can see that there is a tendency to increase, but it's increasing deformations, but it's really slow comparing to the slope without vegetation. So I think I can ease Juan. This is the last slide. So generally, we saw a very close interaction between pore pressure developments and movements of the slope in the field. So if you want to design an early warning system, I strongly suggest to combine these two together. So not only measure deformations, but also measure pore pressure changes. We could see actually precursors of movements about 2 hours before the main failure. Normally in literature, you read that for these type of slopes in the silty sand, you have a sudden failure, but it's not true. It's you can get some information before that. The other point is the basic interaction between the bedrock and the slope. In a lot of publications, also unfortunately in a lot of governmental offices, when they want to develop hazard maps, they assume that the bedrock is parallel to the slope. But in reality, it's very rarely the case. And what we saw was that the shape of the bedrock and also the hydraulic interaction of the bedrock and the slope made a huge impact on the behavior of the slope. So I have put a couple of references. I have given the the slides to Alex, so you can have them. And if you are interested, of course, you can have a further read. And if you have any questions, you can send me an email or ask now. Thank you very much.
Thank you. I mean, I think now the audience know, like, to be a good physical modeler, you are not only to be a good geotechnical engineer. You should also be a mechanical engineer, a photographer, and also a farmer, maybe. So, but because of time, I think we save the question for the last, and we directly let the Dr. Stefano start and